In this video, I'll be talking about, in fact, this is the video regarding derivation of lande splitting factor, and we are talking about we're talking about the magnetic moment of atoms whose valency is one, who have one electron in their outermost shell. And the target of this video is basically to obtain an expression for lande splitting factor, and this factor is very important in understanding this splitting of this splitting of lines when an external magnetic field is applied, and what's generally called as Zeeman effect. And to start with, we are already aware about the magnetic moment, since we understand that electron is revolving around the nucleus, and it has orbital angular momentum. Now, if it has orbital angular momentum, it has orbital magnetic moment, and there is a relation between orbital magnetic moment uh, and and orbital angular momentum. This mu L is a representative of the orbital magnetic moment of the electron, and L is the orbital angular momentum of the revolving electron. And at the same time, we can understand that the direction of this mu L is opposite to the direction of L. And if we go a little bit more from here, we can write down minus E h cross by 2m L by h cross. Now this term is what's called as Bohr magneton. So I should get this negative out, and this whole term, this E h cross by 2m, is Bohr magneton, and it's symbolized as mu b. And so if I have to write down the magnitude of the orbital magnetic moment, mu L, that's going to be mu mu that's going to be mu B L by h cross. So this is the magnitude of orbital magnetic moment. And if we go back to the solution, to the quantum mechanical solution of single valence electron atoms, from there what we have is we have this orbital angular momentum is quantized, and this L is equal to L times L plus 1 h cross, and this small l is called as orbital quantum number. So if I use that this L, I'll get mu L. Mu L will be equal to mu B by h cross under root of L times L plus 1 h cross. This h cross and h cross will cancel, so mu L is going to be mu B under root of L times L plus 1. And this L is the orbital quantum number, orbital angular momentum quantum number, and its value goes from 0, 1, 2, and so on and so forth, up to n minus 1. Now, similar analysis gives us the spin magnetic moment, mu s, and this mu s is minus 2 times E by 2m s. And again, what we have here is that this spin magnetic moment its direction is opposite to the direction of spin angular momentum. And this mu s, it's this mu s can be written, the magnitude of mu s can be written as 2 mu b by h cross and s. And in analogous to the orbital angular momentum quantization, we have the dependence of this spin angular momentum on the spin angular momentum quantum number. And what's that? That is this S is this magnitude of S is under root of S times S plus 1. H cross, and this S is a spin magnetic quantum number. It's a spin quantum number. Now, so what we will have here is this mu s. This mu s will be 2 times mu b, then under root of s times s plus 1. This is divided by h cross times h cross. This h cross and h cross will go, and what we'll be left with, we will be left with mu s equals 2 mu b under root of s times s plus 1. The magnitude of spin magnetic moment is given by this relation. So, this will be the magnitude of spin magnetic moment, and we have already obtained the magnitude of orbital magnetic moment, right? And so we will have the total magnetic moment. Total magnetic moment. And what will be that? That will be mu j. That will be equal to mu L plus mu S. And now, what should we do is we should try to take we should try to take the components of mu L and and add its component with the component of mu S along mu J. So that would certainly require a piece of geometrical work. So let's go with that geometry. I think I need a new page for that. So what I would like to demonstrate here is that what I have is I have mu. No, I'll take this as j vector. So this is total angular momentum of the atom as j vector, and what is opposite to this j vector is mu j. All right, and then what I'll do is I will take mu L. So let us go from here, and so this is my mu L vector, and and this should be L vector because L is opposite to mu L. So this will be my L vector. Now at the same time, from this direction, I'll take S vector. Now this is my S vector, and what is opposite to S in vectorial form is mu S. So this is my mu S. So what we have, we have a triangle kind of thing here, and we would like to take the components. Now we can see here that this is L and this is J, and the angle between this L and J, I will choose this angle as alpha. So if this is alpha, this is also alpha, vertically opposite angles. At the same time, I will choose this angle. This is the angle between spin angular momentum and total angular momentum, and this angle is beta. I'll choose this as beta. Then this angle will also be beta. All right. So so this alpha is what? Alpha is the angle between it is the angle between L and J vectors, and we can also say that this alpha is the angle between mu L and mu J. Right? So it's one and the same thing. So alpha is the angle between J and L, is the angle between mu L and mu J. And beta is the angle between S and J, and at the same time this angle beta is the angle between mu J and mu S. So if I want this mu J, I want this. I want the totality of this mu J. This mu J is going to be what? It's going to be where is L? This is L. It's cosine component. Okay, so that will be mu L cos alpha, right? Plus mu. This is mu L cos alpha, and we will have we will have the cosine component for beta. So this will be mu s cos beta. So mu j will be it will be the summation of mu l. It will be the cosine component of mu l and the summation of cosine component of uh, uh, mu s cos beta. Right. So now let's go with the. So this will be my equation. I'll call this as equation 1. All right. Now, I can use what I have here is basically this is my J, this is my L, and this is my S. All right. So this is J, this is L, and this is S. And what is J is J is opposing the two vectors. So I can use triangle law of vectors here directly. So I can write down this total angular momentum J. This J is the vector sum of L vector and S vector. L vector and S vector. Okay, if that's the case, I can write down this S vector is J vector minus L vector. Now, now if I take the dot, if I write S dot S is J minus L dot J minus L. So this is going to give me S square. This is going to give me J square. LJ, L dot J, and J dot L, and that will give me minus twice L dot J, and minus minus plus L square. So I can turn down this twice L dot J as on the other side. So I'll have J square plus L square. I'll turn down this to this side minus S square. So L dot J is basically LJ cos. So what's the angle between L and J? The angle between L and J is alpha. So this is cos alpha is J square plus L square minus S square. So so I can calculate cos alpha will be J square plus L square minus S square divided by uh, 2 times. Here we have 2 times. So this will be 2 times magnitude of L and magnitude of J. And we know from quantum mechanics that this J square is J times J plus 1 H cross square. And same is the case with L square is L times L plus 1 H cross square. And same is the case with S square is S times S plus 1 H cross square. So I can use these values in this equation and I can find this cos alpha is J times J plus 1, then plus L times L plus 1 minus S times S plus 1 times this whole thing is times H cross square whole divide by 2 times. For L I have under root of L times L plus 1, but H cross is outside the root, and under root of J times J plus 1, and H cross is outside. Now this H cross, and H cross square will cancel. So we will have cos alpha. So what will be cos alpha? This cos alpha will be J times J plus 1, then plus L times L plus 1, and minus S times S plus 1, whole divide by 2 times under root of L times L plus 1 under root of J times J plus 1. That should be the case, and this H cross square is out. We have got the rid of this this H cross square. So cos alpha is equal to all this that we have, and now similarly we can write down cos beta now. making a comparison. By symmetry, we can write down cos beta. It will be something like j times j plus 1 plus s times s plus 1, then minus L times L plus 1. Okay, in the denominator, I'll have 2 times under root of j times j plus 1 under root of, instead of L, we will have s times s plus 1. So we have written down the value of cos beta by symmetry, but using the same analysis that we have used for cos alpha, you can use that analysis and you can calculate cos beta. So we have cos alpha, we have cos beta, and we can use this cos alpha and cos beta in this equation to calculate mu j. So what we will have is, we will have mu j is mu L, and mu L times this whole thing, j times j plus 1 plus L times L plus 1 minus s times s plus 1, okay, divide by 2 times under root of L plus 1 under root of j times j plus 1 plus, okay, then we have mu s. Then this whole thing I have to write, okay, so this is j times j plus 1 plus s times s plus 1, then minus L times L plus 1 whole divide by 2 times under root of j times j plus 1, then under root of s times s plus 1, and close the brackets. All right, so this is the situation, but we have already calculated this mu L in terms of Bohr magneton, and what is this mu L and mu S? These things we have already calculated, and would like to see that. So what we have for mu L, we have mu B under root of L times L plus 1, and for mu S we have to have 2 times mu B under root of s into s plus 1. All right, so let's go with that and use for mu L and mu S, and see where we will reach from here. So what we will have is mu J now. So I will have mu B under root of L times L plus 1, and then the whole thing times j times j plus 1 plus L times L plus 1 and minus s times s plus 1 divide by under root of 2 times under root of j times j plus 1, then under root of L times L plus 1. Okay, so this is with mu L, then plus 2 times mu B under root of s times s plus 1. Okay, then we will have the bracket, and this whole thing will be there. What's that? J times j plus 1 plus s times s plus 1, then minus L times L plus 1 whole divide by 2 times under root of j times j plus 1 under root of s times s plus 1. Okay, till now it's fine, it's going okay. So we have what we have here is we can see that this term will cancel with this term, and this term will cancel with this term. So what we are left with is mu j is mu b times. Okay, so here we will have 2 times under root of j times j plus 1. So this will come as mu b will be outside. Okay, let me differentiate this. So mu b will be outside, so we will have the LCM here. What will be that? That will be 2 times under root of j times j plus 1. Okay, then we will have this whole thing and this whole thing 2 times. Okay, so this is 2 times, we can see here, this is 2 j times j plus 1, j times j plus 1. This will give me 3 times j times j plus 1. Okay, that's fine. Now what I have here, 2 times s plus 1, it will be subtracted to this, so I'll get plus s times s plus 1. That's fine. Now here I have 2 times L plus 1, and this is the sign is basically negative. So here we have positive. The 2 will be subtracted, so we will have negative L times L plus 1. That should be the case. Okay, so this is mu j is mu b times 3j times j plus 1 plus s times s plus 1 minus L times L plus 1, divide by under root of 2 2 under root of j times j plus 1. Now we can write down this equation as mu j is equal to gi and mu b under root of, yeah, that should be the case, under root of j times j plus 1. Now this term that has been introduced here, this gi is called as lande splitting factor. And we can understand here that what we have done, basically, we have rationalized the denominator here. So we have multiplied and divided by under root of j times j plus 1. So that way, in the denominator, what I will have will be 2 times j 2j times j plus 1, because when you'll multiply the denominator by this factor, it will be whole square of this, so you'll be left with j times j plus 1. So this gi is called as lande splitting factor, and we can write down its expression now, and what will be its expression from this point of view? It will be this whole thing divided by 2 times. The root is gone because we have rationalized its denominator. So what will be the what will the result for this lande splitting factor, which is very important in understanding the splitting of lines, spectral lines, in case of Zeeman effect. So this gi, the lande splitting factor, is going to be till now we have reached 3j times j plus 1, then plus s times s plus 1, then minus L times L plus 1. This is whole divided by 2j times j plus 1, because we have done rationalization, and rationalization has given us gi equal to this whole thing, but there will be no root available here in this case. Now we can make a further little simplification here. It would be like if I write here 2j 2j times j plus 1 divide by 2j times j plus 1. I can do this plus j times j plus 1 plus s times s plus 1. All right, and then minus L times L plus 1. This will also have the denominator 2j times j plus 1. If you add the 2, you'll get the same thing. That's over here. All right. So the lande splitting factor g will be 1 plus j times j plus 1 plus s times s plus 1 minus L times L plus 1 divide by 2j times j plus 1. So that's the end of the story. So what we have done, we have achieved the expression for lande splitting factor. Now this gi is called as lande splitting factor. So with this, I would like to say goodbye and have a nice time. May God bless everyone.